In this section, we will apply dynamics in Newton's laws in order to study the phenomena of apparent weight, which surely you've felt if you've ever been in a car that's accelerating, or you've ever been on a trampoline, or you've ever been on an elevator, or you've ever been on a roller coaster. Apparent weight is quite common, so let's learn what it is. So, if you have ever been something that's accelerating, say like a rocket ship, which is quite uncommon, or a car, or a roller coaster, or an elevator, you'll notice that when an elevator or car accelerates, you'll feel a little shift in your weight. Maybe you get a little bit lighter, or you get a little bit heavier. If you're on a roller coaster, when the roller coaster first speeds up, you'll feel yourself get thrown back in your seat and feel yourself get heavier. Or if you're on a trampoline, when you're in midair, you'll feel completely weightless. So what is this phenomena of a shifting of weight, or perhaps the perception of a shifting of weight, and perhaps it's just an illusion? So we call this phenomena apparent weight. It's the sensation of a change in weight. Please note, okay, as we'll get to in a second, is that your weight's not actually changing. It's an illusion. It's a sensation, illusion, or perception. So it's not actually happening. It's just a sensation and illusion that you feel, and we'll study what causes that sensation. Hence why we call it apparent weight, because it's what your weight feels like it is, even though your true weight is not actually changing, as we'll see in a second. So a trampoline example, when you're in midair, you feel weightless. The force of gravity is still acting. So as I just stated, the weight is still the same because the weight is a measure of force due to gravity. So your weight does not change, but you feel like you've become weightless. Your apparent weight, you would say, is zero. So if we take note of what's happening here, when you're in midair, the force of gravity is still there, so your weight's still there, but there's no normal force from the trampoline surface. Now, if you're standing on a trampoline, you'll feel your normal amount of weight. The force of gravity is still acting, but now there is a normal force. So what we come to conclusion is that the normal force, the sensation of weight that you feel, that illusion of weight that you feel, is a result of the normal force acting on one from a surface. So the normal force pushes up on you, which causes you to feel your weight. If there isn't any normal force acting on you, you'll still have your weight, but you will not feel that weight. And likewise, if the normal force acting on you changes strengths, you'll also feel change in your weight, a perceived change in your weight, even though your weight is not actually changing. So let's look at analyzing situations involving apparent weight. So again, as we just talked about, the normal force is what causes you to feel the sensation of weight. So a typical apparent weight scenario involves determining normal force acting on a person, provided knowledge of the system's acceleration and other forces acting on the person. So let's look at a person standing on an elevator. A person standing on the elevator has two forces acting on them. The weight, or the force due to gravity, which again does not change. I cannot emphasize that enough because, well, the gravity is not changing. The acceleration of gravity remains the same, your mass remains the same, so your weight remains the same. And then you have your normal force, which causes you to feel that sensation of weight acting, that pushes up on you from the ground. So here's the basic analysis that you need to follow for an apparent weight scenario. We use Newton's second law in the y direction, and we note that we have two forces acting, the normal force, which causes the apparent weight, and the force due to gravity, or actual weight. Again, because the force due to gravity acts downwards, that's going to be negative, okay? And that's going to equal mass times our vertical acceleration. Now our normal force is going to be equal mass times our vertical acceleration plus Fg. We add Fg to both sides, and then we substitute in mg for Fg. We can factor out in this step the m to get that our normal force is equal to m times our vertical acceleration plus our acceleration due to gravity. So in these cases right here, this is the step. These are the basic steps that you're going to want to follow in order to analyze your apparent weight. So let's look at applying this to some specific cases. So in case one, we have a positive acceleration. So suppose an elevator is speeding up as it ascends upward. If you've ever been on an elevator as it speeds up and heads upward, you'll notice you'll feel a little bit heavier. So in this case, the acceleration is going to be positive. We'll call some positive number plus a. So in this case, a plus g is going to be larger than g because we're adding on to g a positive number. So this indicates, as a result, in our subsequent equation, that the normal force is going to be greater than the force due to gravity. So when the acceleration is positive, you'll feel heavier. Now we move to case 2, zero acceleration, where we're in a state of constant velocity and hence dynamic equilibrium. So in this case right here, let's say the elevator is ascending at a constant velocity. So after an elevator has sped up, if you've ever been on an elevator, it returns to a constant speed. And in that case, you'll notice that you feel your apparent weight shift back to what you feel when you're just standing on the ground. So in this case, when you're moving at constant velocity, the reason why is that when you're moving at constant velocity, your acceleration is 0. So the equation that we just derived reduces down to just mg. So as mg is representative of the gravitational force, this tells us that when the platform is moving at constant velocity, our apparent weight remains unchanged and is equal to our actual weight. Hence why when an elevator is moving upwards or downwards at a constant speed, you feel your weight as it normally is when you're standing on the ground instead of feeling heavier or lighter. And lastly, when we have negative acceleration, if our elevator is still ascending, but slowing down, the acceleration is negative, what we'll call negative a. So as a result, we're subtracting away from our acceleration due to gravity, so negative a plus g will be less than g, which indicates that our normal force is less than the force due to gravity. So when the acceleration is negative, you're going to feel lighter as a result. Conceptually speaking, what's happening is that when your elevator is ascending but slowing down, you're going to be losing contact with the floor of the elevator, and hence the normal force decreases in strength. So as a result, the normal force will be less than your force due to gravity, and thus your apparent weight will be less than your actual weight. You feel lighter than you actually are. So all these cases of apparent weight shifting has to do with the amount of normal force acting on you. If you feel heavier, then it means that the floor is pressing more against you, and thus the normal force is stronger, thus causing you to feel heavier than you actually are, which again corresponds to case 1 when we're positive acceleration. If we're moving at constant velocity, that indicates that the floor is pushing on us just as much as if we are standing on the ground. So we're in a state of equilibrium, and hence the normal force is going to be equal and opposite to the force due to gravity. So let's match math to reality here, okay? So an elevator is descending when it begins to slow down at a rate of 6 meters per second squared. If a person has a mass of 84 kilograms, what would be a normal force acting on a person during this part of the elevator's trip? So one thing that's helpful for us to visualize whether our acceleration is positive or negative is before we draw the free body diagram, just to draw arrows depicting the velocity and acceleration, okay? So we're descending, which means our velocity is heading downwards, and we're slowing down, which means our acceleration must be opposite the direction of our velocity. So our acceleration must be heading upwards and thus positive. So in this case, we would expect that our weight, or our apparent weight, the normal force acting on us, is greater than what our weight actually is. So again, we apply the same setup. We have the normal force minus the force due to gravity equals mass times the vertical acceleration. We solve for the normal force by adding Fg to both sides, and we get MAY plus Mg equals our normal force. Again, we factor out the M, and we go through a little bit of algebra, and we plug in our known information. So we have 84 kilograms times 6 meters per second squared plus 10 meters per second squared tells us that our normal force is 1,344 newtons. For reference, if you calculate out your actual weight in this example, you're going to get 84 kilograms times 10 meters per second squared, which is 840 newtons. So it matches what we'd expect to happen, that we would expect our weight, our apparent weight to increase. You can see that even I mess up the wording sometimes, so you need to be very careful with that. That your weight does not actually change, but it's the normal force that acting on you that does change, causing you to feel heavier, even though you're not actually getting heavier. So in this case, it would correspond to that as you move down and as you descend and slow down, the normal force acting on you grows in strength and presses against you more, causing you to feel heavier. Oh, 1344 newtons, not 840 newtons. That's your true weight. I keep messing up. Again, normal force, apparent weight. It's just an illusion. Your true weight remains the same, always and forever, unless you move to a different planet. And this concludes our lesson on apparent weight.